turned on. Is that better? Doesn't sound any different. Oh, because we're probably not on the mic. There. You have to hit that one. And up. And that should do it, right? A little bit better? Yeah. All right. Well, that's okay. It's close. So in solving these that are continuous over several supports, there are different methods. This presents three, and they're actually very similar. They're based on, the first one's based on a superposition using deflection. This is what we did here, where you consider that middle support as if it were a load, right? Here, the super deflection is based on here, the total case, and then is a sum of the case with without that center support, and then you add in the center support separately. So that's the addition there. And then you can solve for the deflection of each of those, and in the case of the bottom one, the support is an unknown. So when you solve for it, you have that P in the equation. Hey, here we go. Look at this. Where'd it go? Now it's not going to work. Wow, is that weak, huh? All right, yeah. All right, maybe it's better with this. This P is the unknown. So you solve it and you're able to find that P. Once you get that reaction, then you can go ahead and it's determinant from that point on, right? You can go ahead and this is the example we did. Once you get this reaction right here, then you can solve the problem. Then you can build the shear diagram, the moment diagram. So it's the reactions actually that allow you to solve the whole problem. I mean, once you get all the reactions, you know, it's just smooth cruising after that. The second method we looked at, this is the one that we talked about, this diagram for a situation, a moment alone without any load on it. So this as a loading. This moment is a loading which causes a constant shear. These are the end reactions. It'd be, right, this is this case. If I twist one end of it, and then I'd have to hold the other end down, that's that downward force, and it's balanced by that force. And then you get these diagrams using that information about the slope. We derived, actually I think I derived, didn't I, in class? This formula. Engel derives it, certainly. You can look at that. And using this formula, then, it's just a matter of kind of plug and chug. Yeah? All right. How about that? Then it's just a matter of plugging in the numbers and cranking out the answer, which we did, right? This is the example of that. Okay, sweet. And then you go, okay, this is interesting. Once you get what you solve here, you come up with, okay, can I do this? That moment. That's what comes out of this equation. Here's the equation. These things, you get these formulae out of the back of the book, right? This is the slope based on this load case. This is the slope based on that load case. So they're formula that you put in there, and fill in the blanks, and you're able to, whoa, suddenly I'm alive. What happened? I feel like I'm about to explode. Take that off. All right. Like your ears suddenly open up. Okay, all right. Maybe my battery's connected. But my mouse died. Oh, there it is. Okay, so what you get out of this thing, you solve for the moment. There it is, and there it is. And once you have that moment, then you can go ahead and plug it in here as a free body to fill out this superposition on free body diagrams. So this is the whole beam broken into 4 pieces. 1, 2, 3, 4, right? And here's the moment in the center. Here are the loads separately. And you do that so you can calculate the end reactions. That was calculating the end reactions once all the end, this is going to drive me crazy. I can't be this loud. I'll wake people up. Okay, sorry, I don't want that. All right, relax. Once you get those end reactions, then you're on your way. You get, these are the ones down here, 19, 66, 16. They go up here, right? And once you have this again, then you build the rest of it. Then you're on your way. Now, the third way, and this is, I guess, the most versatile, because the first one was the least versatile. It was probably the easiest, but the least versatile. It had to be symmetric, had to be two spans. The second one was a little bit more versatile. It had to be two spans, but it didn't have to be symmetric. So you could have asymmetric load, asymmetric spans, but they had to be just two spans. This one, now you are really getting the full power. I mean, look at the size of that equation. Whoa, this is something you could get your teeth into, right? Okay, you can do this over any number of spans. You can do it over, over two spans. You could do it over 3 spans, 4 spans, 5 spans, as many spans. This thing is, you could start a beam going all the way around the world and come all the way back, and you could solve it somehow with this, but it'd take quite a while. Anyway, the way this is set up, it makes use of, and maybe we'll turn the lights on just one more time. It makes use of this equation. It's based on, you can see up there, whoops, sorry, you can't see up there in the video, but it's got this case twice, and it's a superposition of this weightless case. This is one where the moments are at both ends, but there's no other load, just the moments all by themselves. And you can see it's the same as adding this and the mirror image of this. So it's like this plus this, right, equals this. And somehow you can see how this would work out with if I add an up here with a, this would be, they're mirrored, right? So here I'd have, if I'm adding over here, I'd add an up and a down. So these cancel out. So that the reactions actually cancel. There are no reactions. You just have to imagine it as and this is, I think, why Engel refers to it as a weightless stick. It's just kind of floating in space. There's no end reaction. It's kind of a fictitious thing, but it's useful in doing these calculations. I mean, in and of itself, it wouldn't exist, right? It's like a, what else would be like that? A unicorn. I don't know, a unicorn may not be the best analogy. Something that's there's a word for that. That's a Eselbrücke, but I don't know what it is in English. When you have something that leads to another thing, but in itself it doesn't exist, but it's a stepping stone to another concept. Right? Okay, so that's kind of what this is. So, this by itself wouldn't really stand up, but you can use it as in terms of superposition, stripped out of another case, and add it together with actual supports in there, and then it is useful. Anyway, so this case then has 0 shear. It has a constant moment, and it has a constant slope. It's circular, I guess, right? It's, I mean, that a constant slope, wouldn't that mean it'd have to be a circle? I think so. It looks kind of like a circle, doesn't it? Look like an arc of a circle? Okay. So that would be this. Now, I'm not going to go through the derivation because it's already one after, but it's very similar to the way I built up the other slope formula. Okay, now you better turn those back off. And you get this lovely formula, and it has 3 supports in it, and it assumes, or it doesn't assume that there's 0 on any of them. I guess it assumes there's a moment. So you've got MA refers to A here, MB refers to B here, and MC refers to C here. And this is span number 1, and this is span number 2. Now, what you do is you work this equation maybe several times, depending on how many spans you have. If you have, like in this example, it shows 3 spans, then you'd have to work it twice, because you see it only involves 3 of the supports, right? A, B, C. So then I'd have to move it over again and work it here, but the middle 2 overlap, so that it gives me there's a situation in there where you will get a simultaneous equation with the same variables that you're able to solve. As you will see, I mean, it's probably easier to demonstrate than to explain. Here it is. It moves over again. You can read all this maybe slowly if it's helpful, but I think it's probably better I just demonstrate it, right? Okay, so here's a demonstration. All right. It's got 1, 2, 3 spans, right? It's got 3 different loadings. They're all asymmetric. Now, maybe you better turn this back on. Turn the light on. Let me see if I can do this, that this makes sense. You have to relabel these things for it to work, and you have to keep track of what you label. So up here, somewhere you have to have a base reference and call these, probably number them, 1, 2, 3, 4. And then in the equation, you're going to call them by different names. So this is, you can think of it like this. This is the real name, 1, 2, 3, 4. That's their real name. And A, B, C are their temporary names. They're just given those names for the equation, but tomorrow their names will be different, or they're depending on where the equation is in the problem. So, okay, let's say we have this, let's say we have that. Oh, not even in the center, sorry, there. And let's say we have this. Now, the first time I work the equation, and what is that equation, by the way? Holy smokes, oh, it's hardly, I don't know if I can write this all up here. M-A, wait a minute. Give it to me somewhere where I can see it a little closer. Well, this is too close. Okay, never mind. Yeah, read it off to me. Wait a minute. Okay, now I can see it. Okay, good. M-A-L, 1 plus 2 M-B L1 plus L2 plus MC L2 equals 6 EI theta, whoops, that's a Q. I'm not getting there. Q theta 1 plus EI. Now these equations here, these two come, these are formula that you've got to look up based on the load case. Now, the first that you're going to work this equation maybe twice. The first time you have to make it a little renaming here. A, B, C. This is L1, L2. Okay? So this goes, you know, this is referring to that. This is referring to that. This is referring to that. You see, like that. And these, the 1s and 2s here, right, they refer to the spans. So this is that one there. Let's call, I'll just abbreviate it, theta 1. And this is theta 2 over here. Okay, on the 2 different spans. Like that. So you fill in those values here. Now when you fill them in, you'll have too many unknowns. You'll have, in this case, MB, in this case, whoa, in this case, this is kind of nice. This one on the end, I do know that one. Sometimes you know some. So this one goes away because this is going, the moment here at the end is 0. But the moment's not 0 there, and the moment's not 0 there. So these two are unknowns. So you've got 2 unknowns in the equation. It's a nice equation other than that, but it's got two unknowns. Now, you redo the whole thing again. I was hoping to do it with a darker pen. Maybe it's okay. Should I write this all up here again? No, I'll tell you what. Well, I'll write it all up there again. How about this? Okay, now, the second time through it, now you shift everything over here. Now, this becomes A, this becomes B, this becomes C, this is now L1, this is L2, this is theta, 1, this is theta 2. So the whole thing shifts 1 over, right? And now your A is still A, your B is B, but see, they're different ones. Okay, now when you put these in, you don't write them. I mean, you'll get totally mixed up if you have to give them their real names, not their fake names, right? The A, B, C are their fake names. You got to give them the real names. So this would be, this one was 0. Doing it with the blue, this would have been M2, right? This would have been M3. All right, and so forth. Okay, I suppose maybe you should keep track of these too, as span 1, 2, 3. Well, maybe you can keep track of what those are. But these actually go in as real numbers, right? You know these distances. These are the only unknowns. The other things all get plugged in as numbers. Now, when you come back the second time, now this is M2, right? This is M3. This is M4. M4. Hey, they're in order. M4. You see what's going on? This isn't confusing, is it? Okay, good. So you work the same problem. The equation has it in ABC, but when you enter it into the equation, you have to do it in 1, 2, 3. And when you do it in 1, 2, 3 instead of ABC, then you'll see the variables that repeat. In this case, 2 and 3, right? Oh, what happened to 4 here? Yeah, 4 would be a problem, but 4 fortunately is 0. That one's 0, that one's 0. So my 2 that repeat, I'm going to have an equation here that has M2 and 3, and I've got an equation here that has M2 and 3. So I've got 2 equations and 2 unknowns. This has got to work. Turn the lights off. All right, so having said all that, the example here would be, whoa, all right. So here we got it, right? Here in reality, called R's here. R1, R2, R3, R4. That's their real names. In green, you see their fake names or temporary names. Let's call them temporary names. Temporary names. Equation names? I don't know. Temporary names. A, B, C. Okay, so A goes to A there, B goes to B there, C goes to C there. You've got to fill in these values. Here are the theta 1 and theta 2. This is a formula coming from the back for this case. Okay, you plug in those numbers and you just get a number. It's just a number. Isn't that wonderful? It doesn't have any variables or anything. It's just a number. And here you plug in the numbers in this one. Make sure you get the right equation. Wow, is that it? 5 over 81? What kind of equation is that? Okay, it must be for that end of an asymmetric single point load. Wow, I hope that's right. Okay, and that goes in there. Then those values come down here. See, they plug in here. And mostly, it's just a lot of plugging in values. These values, you know, the L's, 12 feet and 30 feet, they go wherever they go. Add it up there, singly there. Oh, where's this equation? But the two variables, M2 and M3, they just hang in there as variables. They're going to be, you don't know, that's what you're trying to solve. So those two moments, but give them their real names. Don't call them MB and MC for MC. No, it's M2 and M3, right? Named after their reactions, R1 and R3. Okay, so then what? Then I guess I solve this for one of the two. Picking M2, you solve it. This is just so I can solve the equation. Now, looks almost the same, doesn't it? No, it's not. Look, A, B, C. It shifted over, right? Now, in the equation, in that big equation, wherever the heck it went, M2 is now A, not M1, which was 0. M3 is B. There it is, see? M3. And where the heck is M4? Oh, it's 0 right there. We don't even bother to write his name. It's a little 0. He is 0. So you run through the whole thing again. This time you're on the other side, so you probably get a different equation. 481s instead of 581s, I guess. I don't know, whatever. So that comes out, you add those together, you put that, divide by 6, move it over to the other side, and you can solve it for those two same variables, right? M2 and M3. Putting it, come on, where'd you go? Putting it equal to M2. So then if I've got this one in terms of M2, I had the other one in terms of M2. Come on, where'd you go? Here you are, M2. So I can just equate the two of them. There they are equated. M2 then is out of the picture, and I can solve for M3. Once I get M3, oh, M3, I know M3 now. Well, then knowing M3, I can plug M3 back into, say, this equation here. Where is it? There. Okay, so I plug it in there, and then I can solve for M2. So I got M1 and M2, and no, I got M2 and M3, and M1 was 0, M4 is 0. So now you've got all the M's. Now you can start solving these end reactions. Now, next step, once you get all the moments solved, now you have to build little free body diagrams to calculate the end reactions. Now you'll be able to do it because you know the moments. If you'd done this step first, you wouldn't have been able to solve these free body diagrams because you wouldn't know what M was. See, look, M comes in here. There it is. M. There it is. That's not it. No, it must be 198.7 something. Kip feet probably. Okay. So I make this free body diagram. There's the end reaction R1. This is the first piece, right? What am I doing here? It's this piece. And I've cut it ever so cleverly. Just this side, these are considered to be knife-edge supports. And I'm one infinitesimal, half of a knife blade, this side of the end reaction, which means my R2 is not on that free body diagram. It's out of the picture. But what is the shear. That half arrow there, that means that's shear. So the shear is there. It is essentially 12 feet. The R1 is there, and the moment is essentially, because it's only an infinitesimal off, right? Anyway, 40.5. No, that's not right. 198.7. So you get that, and now what's unknown? Well, actually, the shear would be unknown, and this is unknown. Well, it's just like a simple beam then, right? It's what you always have, or two end reactions out there that aren't known. So you can just sum moments about one end and some moments about the other end, and you can solve it. And the only interesting thing is that this end has a moment on it somehow, so you don't forget to put that in there. So when you saw here, I'm solving about M2 or R2 rather. I'm summing moments about this end here. There it is. There's this end reaction, which I don't know what it is, and here's the distance, force distance minus, that's going clockwise. This one's going anti-clockwise. There's 48. And then you got to put this one in, which is going clockwise. See it going clockwise, which is a negative moment then, right? Which you expect, and you get that. You get the first end reaction. You got that one. You can solve vertical forces and get the other shear. So now you got both of these. Now you can take this. You have to work these sequentially because you needed that to go to the next step, I think. Don't you? Seems like you probably do. So having that one, yeah. Here's the next free body diagram. This is the middle section. Now I've included, I've cut it at the same place this one was cut, but on this side of it, the reaction shows up in there. So I've got the shear because I'm cutting it just that side of the, what you never really want to do is, this would be very foolish, cut a support in half. Not with free body diagrams. Never cut a force in half with a free body, although it kind of looked like we did that on the other day, but I don't think we did. We somehow superpositioned the whole things in it. Okay, so this is a free body diagram, and there's that shear that we just calculated. Now look, it's going the other direction. Whoa, that's interesting, isn't it? Okay, because it's on the other side, I guess. Anyway, yeah, because if you put these two together, those would cancel out when it glued back together, right? Here's the moment, also in opposite sense, right? This one's going that way, this one's going that way, but think about it, it actually causes the exact same moment. The arrow, the rotation looks different on the, because you're looking at free body diagrams at different ends of the beam, but the effect on the beam is it's bowing it upward. You know, on one end I'm twisting it this way, and the other end I'm twisting it this way, but it's all bowing up. I mean, that's a negative moment. So it's the same negative moment. It's got to have the same effect. So that's, come on back here. All right, so that one's right. Now we stick this one on the other end. We know what that one is too. Hey, swell. And here we're cutting it again right before the reaction over here, before R3. So we get a shear. So we got known shear, unknown reaction, known moment, unknown shear. Two unknown essentially support forces, vertical forces. So it's the same thing over again, and you get R2, right? You some moments about here, and you get R2. That's what this is. Then you could vertical forces. Seems like there are more vertical forces here all of a sudden, but I can solve for this shear here, and that's that. Now I've got those two. So now this one comes down there. Okay. What was it anyway? 18. 18, yep, it is 18, it's over there. And then now what's left? Okay, this one we don't know. Suddenly that one shows up, and here's the one at the very end. And there's no shear out here. So good, we can whack it all the way to the end. Again, only two unknowns. So that each one of these little pieces, I take it, I cut it so that I've just got two unknown verticals. And it just repeats again and again. And it's just, in terms of solving it, it's the same as how you always solve these simple beams. There's essentially a simply supported beam with a little moment on the end. So that now, what do we got? R4, R3, where did R3 go? Oh, there it is, R3, R2, R1, you got all the R's. Good job. So you put all the R's on here. There's 1, 2, 3, 4. Now you've got a completely defined load diagram. You're almost finished. All you have to do is follow it down, building it the same way you'd always build a shear and moment diagrams. So this is starting out at something, what does that say there? 7.4. 7.4, oh yeah, 7.4. And you've got, man, where does this mouse go? Okay, here it is. You've got this constant load, so it's constant slope. Then you've got no load, so, but you do have this end reaction, jumps up by that end reactions. Interestingly enough here, look at this. As you work your way across, I mean, if it were me, I'd just build it the way I always build it. But you can go back and you can kind of check these values. You could say, hey, wait, where have I seen this guy before? 40.56? Wait a minute. That seems so familiar. What? 40.56. Yes, it's that. There it is. And this other one, 41.03. Oh, we didn't look at that one, though. What we did look at, I think this one, didn't we? Well, 18.97. That would be that guy right there. 18.967. Okay, good. Hey, nice. All right, so you get all those, and then you can build getting areas. You can get the moment diagram. Now these again you can check. Look, 198.7. Where is that? That came from these equations here. There it is, 198.7. M2. Here's M1, 0, M2. So they check out. So you got to check them out. This one we would have to get through areas. I guess that one's a pretty interesting, in fact, whoa, yeah, that's probably the most interesting one, right? It's the biggest one. Okay, so I guess you have to build this diagram to get that one, because that one didn't come out. That's not an end reaction. See, that's a positive moment out there. These are all negative moments. The other thing that's kind of interesting, you can turn the lights back on, is you notice there are almost always negative moments over an interior support. You got an interior support like that. You got loads on either side. It's going to bend it like that over the support, right? If it bends it like that over the support, that's tension on top, compression on the bottom. That's a negative moment. So all those, that one and that one, those interior supports are going to be negative. Now the other ones in between, they probably go positive, but they don't have to go positive. You could have a scenario, can't you? Seems like you could have a scenario. Maybe it takes another span. Okay. That if I put a real heavy load here, try to picture this. If I put a heavy enough load here, that center span bows up. If the load in the center span is not very much. Also, the other way to get it is to do that, have bigger spans, so that instead of having a positive, this might not come up that high. It might only it would come up like that maybe, even if it were a point load. Or if there no load, if there had been no load there at all, that's 60. If it had just been gone, then this would, I guess this would go across like that. It wouldn't change. Yeah, well, it'd change maybe in slope or something, but it wouldn't have a peak there. All right, well, that's nice. Okay, here are a couple of cases that are interesting. I don't know. I was going to work these out, but I don't have time to work them out. But I'll show you what's interesting about them. Here, turn that light off. This is another one that's 3 spans, right? And you could work it the same way we just worked it, but you wouldn't have to work it that way. There is a, well, I mean, you could do it. If you started to work it, thinking you were going to have simultaneous equations. I mean, you look at that and you say, okay, I think I see 3 spans, 1, 2, but one of the spans is actually a cantilever. So when one of the spans is a cantilever off the end like that, actually you do know the moment that would be caused by that. That thing on the end, if I drew a free body diagram just of that, here, turn my lights on down there. If I drew a free body diagram just of that, oh, wow, blinding. And there's a pen doesn't work. Another one that doesn't work. Get out of here. One of these work, isn't it? Okay, well, let's say we did this. It works enough. Okay, so there's 15. Okay, I'm cutting it here. I'm cutting it in front of the support. Here's the support. It's an infinitesimal on this side. So I cut it just before that support. Well, what the heck? I could cut it right on the support. It wouldn't matter in this case. But the important thing is I've got what? I've got a moment here that has to hold that up. I've got a distance. What the heck is that distance? Does anybody see it? 10 feet. Okay, 10 feet. So I can sum moments about this point here, and I get this moment. See, this is, let's call this 1, 2, 3. Okay, let's call this 3. All right, so if I sum moments at 3, I mean, this is just a cantilever, right? I'd have m, which is going to negative m there, and then I'd have this, which is going positive 15 times 10. Didn't look like the bracket I wanted. 10. Okay, so then m equals 150. 150. So 150 with this sense, which is a negative, right, is going to be. So actually, I do know, who is that anyway? A, B, C. I know that one. I can plug that value in. That's why I just figured. That's 150. So that's 150. That's not an unknown. this one I also know, right? In this case, this one is 0. So when I work this equation, I plug 0 in there. That goes away. I've got, this is an unknown, MB. I have to put the spans in there. There are only 3 spans, A, B, and C. Oop, okay, these 2 spans. I'm sorry. I'm working this span and this span. That's 1 and 2. But C is in it, the third reaction. But I just solve C, and I get those. So I can solve in one shot. There's no iteration there. I can get it in one shot. The other case that might come up is a simplified case. This one has no cantilever, but this one has the unique quality that it's symmetric. It's absolutely symmetric, right? So before you ever even work this, you'd have to know it's going to come out symmetric. That 25 there had better be balanced. I mean, it better mirror a 25 over there. The end reactions, that 50 and the 50 have to mirror. Also, the moments mirror. Look at this. They do. 120, 120. So when you do this one, and you work the equation, okay, this would be MA up there. That's going to be 0. This one, you can call it something. You can call it M2 maybe. But when you come to this one, you know, I mean, it's really M3, but M3 equals M2. So you could call it M2 if you wanted to, or just call it M. Call these both M. At any rate, B and C are going to be equal. So knowing that they're equal, you're not going to have 2 variables. You're going to have 1 variable, that M. So that you could plug these in, plug that, and this will be the same. So you can solve it immediately, and it'll come out for that 120. Well, that's an exciting bit of news, I guess. All right. Anyway, you can try he gives quite a few of these in the book with numbers attached to them, and there's several in the course pack. So I'd try a couple of them. Make sure you know how the patterns go. You know that in different cases with the cantilevers on there. I think the one on the course pack's pretty. I mean, the one in the computer is very straightforward, normal 3 span or 4 spans or something, whatever it is. All right. So I'm sure you'll get to do some more.